All right, so we'll go ahead and start. For 10 on yesterday's homework, if you just simply plug in the x's or the x or the quantity, because it was actually a quantity, and then you take the derivative of that quantity, you get that top one. Okay? And that answer is fine. It does take it on WebAssign, but I just wanted to show you. You can actually then take this quantity, because you're multiplying, and put it in the numerator. Kind of put it over 1. And then if you write it like this, you can cancel 2 x's in each spot. And so that's why that is the best answer, or just the reduced answer. Okay. The top one WebAssign takes, and that's fine. But I just thought I'd at least show you that you can actually do some simplify. I think this is the only one that you could simplify. Then there was one where you could distribute, which I think we talked about in class. But this one you can actually do some simplify. All right, so that was 10 on yesterday. Okay, so today we're going to do we're going to go to section 4.5, part 1. And it's called U substitution. Substitution. And today we're going to do it with indefinite integrals. All right, let's remember what is indefinite. So U substitution, that's our new method. That's the method we're going to use today. It's kind of like the quantity rule for when we take the derivative for differentiation. It kind of fits that in general. So U substitution, another rule, another method once our problems get harder and we have to take the integral of harder problems. So U substitution we use a lot, but it doesn't work all the time. And what does indefinite integrals mean again? Indefinite means our answer is the equation that would find us the area. We don't have a start and stop. So that's kind of nice. The problems are actually shorter. We're not going to have numbers to plug in to actually go find the area. We just have to find the equation. Okay, so two reminders, and then we'll actually go to U substitution. So just two kind of reminders. If I'm taking the integral and I have a constant, a number, f of x and then dx, this number, as long as I'm multiplying, can go out in front. You don't have to involve it when we're actually doing the integral. And it's more just kind of convenience. It's one less piece that you have to look at. Because U substitution is going to be a little crazy. And so if there's anything that we don't have to look at, the better. Even if it is just a number, it'll kind of be nice to put it off to the side. Now, symbols, the other thing we have to talk about, symbols for derivatives. I know, which is kind of weird because we're talking about integrals, but in the middle of this integral, we're going to be taking the derivative. So mixing it all together. Symbols for derivative. What do we normally use? We normally use this guy, right? It's just short, quick. Every once in a while, I use like d over dx. The one we're going to go back to and use today, though, is dy over dx. Which is really probably the best notation anyways, because what does the derivative find you? Slope, which is the change in y over the change in x. But today, and these are pretty similar. This one just doesn't specify a letter. It's just kind of in general saying, hey, take the derivative. Usually I use this when I put the equation right after it. Where here you use the y when an equation is labeled, like with a y or a function notation. So this is the one, don't forget this means derivative. And notice, remember this is the width of rectangle, which is in fact the change in x. This change in x is the same as this change in x down here. All right, so instead of writing, we're going to go right to examples. Okay, I think it'll just be easier than writing something out for this process. Let's just see what the directions. Oh, maybe I put it in here. Hang on. I use the word evaluate. I don't know if I like that, but yeah, okay, that's what they said, evaluate. So there we go. All right, so let's go through, we're just going to go through examples, but when we do this first example, we're going to learn kind of U substitution as we go through a problem. Okay? And then we'll just keep practicing it. That's the only thing we have to learn, this U substitution. It isn't the greatest thing to write down, so we'll just kind of go through the process. So evaluate. Didn't even put evaluate, we could do evaluate the integral. Let's start with this one. Here we go. The integral of x squared times 10 plus x to the third, all to the fifth power, dx.
Is there a U for that?
No, that's okay. So that we got to create the U and everything on our own. So that's a good problem, or that's a good question. It doesn't start out with U's. We are going to actually create these U's. Okay, good question. So we're going to figure out something that is going to be a U, and then we're going to use that value as a substitution. What else? Okay, notice it's an indefinite integral. Just because there's no numbers here. Okay? So tomorrow we're going to do the same thing, but we're going to have numbers there, which just means longer because then you can actually go find the area. Okay, so you need what is this U substitution? You need to find, remember I said it's kind of like a quantity. You need to find a quantity in this problem. Are you ready? Did you get a picture? Yeah, okay. All right. Do we see that there is a quantity here that's being raised to the fifth power? Okay, we're gonna kind of consider this x squared as just kind of one thing, but we have this quantity, this plus, raised to the fifth power, and that is going to become our U. 10 plus x to the third. Notice I don't take the power of 5. Okay, I just take that quantity. 10 plus x to the third. There's something else I can say. All right, that's okay. And then we actually take the derivative. So then we actually take the derivative of U, we're going to write as du dx. And then we actually take the derivative of this. Derivative of 10 goes to 0, and then x to the third becomes 3x squared. And then we're going to multiply both sides by dx. So now we have du equals 3x squared dx. See how this has an x squared. I know it has a little bit more, but see how this has an x squared and this has an x squared? See how this has a dx and this has a dx? Let's rewrite this as 10 plus x to the third to the fifth. And then I'm just going to put this back here, x squared dx. That step's optional at the beginning. You might want to do it eventually. Some of you will be able to drop it. Some of you might still have to kind of keep it together. So what's the difference? This is x squared dx. This is 3x squared dx. So let's get rid of the 3. We're going to divide by 3. So now I have 1/3 du equals x squared dx. That 3 was an extra piece because I'm always matching it back to my original problem. X squared dx, that's what I want. And I had this extra 3, so I'll just move it to the other side. Now, what does this say? What can I put in place of x squared dx? Yeah, equals means I can use either side, they're the same. So instead of the x squared dx, I'm going to write 1/3 du. So instead of the x squared dx, I'm going to write 1/3 du. Because, so now, remember yesterday we briefly said all these letters have to match. Everything now has to be a u. But what did I say 10 plus x to the third was going to be all along?
U.
A u. So this whole thing is now u to the 5th. Well, that's what I was going to say. I knew there was something I was going to say. The first few problems on the homework, they'll give you this. So look for that on the first few problems, or cover it up, or don't look for it, and see if you can figure out the u on your own. Because on the last few, I think all of tomorrow, you'll have to pick the u out on your own. So at the beginning, they'll give you the u. All right, now we're still not done. We still have to integrate. But look at, instead of integrating this, we get to integrate this. And here's where we can even take this 1/3 and pull it out. And don't let the u bother you. Can you integrate x to the 5th? You can integrate x to the 5th, you can integrate u to the 5th. Okay. But keep in mind, after you do all the substitution, you still have to take the integral. Okay? And you have to make sure that all x's are now all u's. But now what do? Add 1, divide by the new. Okay, so remember now, and it's kind of crazy because here you're going to do derivative stuff. But then here you're going to go back to integral. Add 1, divide by the new. Add 1, divide by the new. We got this 1/3 sitting out there. And then we've got u to the 6th, and then we're going to divide by 6. And it's up to you. You can write it like, if you want to write it as 1/3 divided by 6, you can. If you want to divide the u by 6. Eventually, though, you have to put this together. You can do it with a calculator, or it doesn't cancel because you actually multiply by the reciprocal. So it's actually 1/3 times the reciprocal of 6 is 1/6. And the u to the 6 just keeps coming down. Because now we added 1, so now we're good. Now we don't need the integral symbol. We added 1 divided by the new. So 1/18 u to the 6th. Now we got to do two things. We have to go back. Our problem started with x's. So, if someone just comes, they have no idea what u is. So you have to put the u back in. You have to go back, find your u, and put it back in. So the best answer then is 1/18 times 10 plus x to the 3rd to the 6th. And then, because it's indefinite, plus c. So definitely not a short process. So this is going to take us a little bit longer. That's it, but let's just practice. Each problem can look so different, and it takes a while to get kind of comfortable. Do we see at least why it's called u substitution? U's go in for all the x's, but as you're doing that, hopefully you're condensing things down, making it something that we know how to take the integral, because we really don't have a lot of rules for integral. And so we just kind of substitute, and then hopefully we can use a rule that we already have. Okay, what is this? What is this answer? That's great that we found it. We know we get 100 on the test, but what does that do? What does that equation do? That equation will find us area. Area under the curve. Yeah, under, and we can even, the curve is under this curve, x squared 10 plus x to the third, whatever that graph looks like. Curve just means graph or function. You really should say function, but our book, I think, likes curve. And I don't know why. I'll have to see if there's a reason why they say curve as opposed to function. But so the area under this graph. Okay. The problem is, how come I can't go find the area? I don't know where they want us to start and stop. Okay, or let's put finds, right? Let's do finds area. That's fine. All right, let's try another one with this use substitution. Let's do integral of x to the third times cosine of x to the fourth plus 2, and then dx. All right, so what is, most of the time when you see like a lot of multiplication, that's when you're going to do this use substitution. Okay, so if you see that it's, now remember, this does not mean cosine times x to the squared, x to the fourth plus 2. But we do have multiplication here, x to the third, and then times this cosine. So that cosine is all together. But a lot of times we use substitution when we have that multiplication, which we do. We have that x to the third times at least that cosine. Anyone, and remember the first few they'll tell us. Anyone want to guess or try what our u is going to be? What is something that has something else with it? Like on that last problem, it was kind of a quantity, and it also had that extra power of 5. So what is something here that has an extra piece with it?
Maybe sine x to the fourth plus 2 times 4x to the third.
Not that whole thing. But what has the extra piece with it? Like this had parentheses with a 5. So, well, you might have said, did you want that whole thing to be u? Everything that you said?
Would that be like the derivative? Like the u would just be cosine x to the fourth plus 2?
Okay, then now you're on to something. That's good. Now remember here though, the 5 was not part of the u. So same thing here. Yeah, this has this extra piece of cosine, but don't take the cosine as part of your u. So your u is just going to be x to the fourth plus 2. So don't make it too much. Notice that like on the last problem, we don't take the 5, but because it has that extra thing happening to it, that becomes your u. So x to the fourth plus 2 has this cosine attached to it, but you don't take that extra piece, just like we didn't take the 5. But that signals that that's your u. All right, so let's see what happens. So now we're going to take the derivative. We're going to write this as du over dx. Remember, in the middle of the integral, we actually take the derivative. All right, and then what is our derivative over here? Roll it down, subtract 1, right? So 4x to the third. So roll it down, subtract 1. Now we're doing derivative. 2 goes away. Multiply both sides by dx. And now is when we know that we want to do some substitution. So we kind of have to figure out how are we going to get this to fit our puzzle. We have to actually change our puzzle to force it to fit. So we got to figure out how are we going to change this so that it'll fit. Well, remember, this goes together. So I know we only use this for our u, but now cosine is locked in to x to the fourth plus 2. So that's all taken care of. So what we have left, we have x to the third dx. That part we haven't touched yet. So how can we force this to fit? Well, I have an x to the third dx. How can I make this right side be an x to the third dx? Divide by 4. Now I have 1/4 du, and there it is, equals x to the third dx. And I forced it to fit. You force that right side. The right side is what has the x's. You force that right side to match the rest of your problem. Okay, so now, integral, cosine, but we don't have to write this. What can we write instead? Cosine of u. And then in place of x to the third dx, 1/4 du. This is now going to be 1/4 du. And this is what I was talking about. I mean, you can leave it, but what's that c? That very first thing that we talked about, c is the constant. That 1/4, we don't really have to look at it when we're doing the integral. That number, usually a number will pop up. Usually, not always, but sometimes you do have to divide to get that number. You can just put that off to the front. It'll still be in your answer, but it's kind of like one thing less to look at right now. Okay, then just remember derivative of sine is cosine. And that's the only one we need to do, right? Because that means then the integral of cosine is sine. So now we're ready, after all that work, now we're ready to take the integral. So that's not our answer, but let's just bring it up here. What is the integral of cosine? Sine. Okay, the 1/4 stays. So sine, now the only problem is it's sine of u. And my integral's gone. I just took the integral. Now we just have to replace everything. So my final answer then is 1/4 sine, but u was x to the fourth plus 2, x to the fourth plus 2, and then because it's an indefinite, if it's definite, which we will do tomorrow, then we got to plug in the b, we got to plug in the a, and then subtract the 2. But at least we'll have like a numerical answer. All right, so what does this equation do? This finds us the area under that original function or original curve. Let's do that. All right, let's do this one. All right, so let's take a look. I don't know if it's too early to do this one, but let's do the integral of, it's a fraction, dx over 3 minus 5x squared. So a couple things. Let me look at this. We really only have one thing, which is kind of nice, because that one thing, then we don't have a choice. That one thing will be the u. Remember, don't take the extra piece with it. And it does make sense, though, that it does have that extra piece. Let's just talk about some other ways that this could be written. You could write this as 1 over 3 minus 5x squared, and then the dx off to the side. Remember that dx is just multiplication, so that's why they can put it in the numerator. Don't let that make it look weird. And what else could we do? that because it's in the denominator, we could move it to the numerator. You just have to be careful because then we have to make the exponent negative. Usually we like to write stuff with a positive exponent, but we know that once we go take an integral or a derivative, we like it actually written as that negative 2. Okay, but either way, we only have one piece. Any ideas what our u is going to be? Perfect. We only have one piece, but remember, don't take that negative 2. But it does have something else with it. Like we only have one thing to begin with, but it does have something else with it, which kind of says, okay, yeah, that's a good idea that that's going to be your u, and don't take that extra piece. So yeah, so u is just the 3 minus 5x. Okay, so even though there's only one piece, there really is something else. What is still hanging around? We still have the dx. So we have to make sure that we get everything in terms of u. I mean, if this makes sense, we would have this. This is our u. You can put that in as soon as you decide it. So what's wrong with that? Why can't I just take the integral of that? Not the negative. And we really haven't seen this, but if your letters are different, that's no good. That you cannot do that if you've got some u's and some x's. So just be careful. Sometimes these easier ones, you want to jump to it right away. We still have to go through and make sure everything now is in terms of u. Everything has to be in terms of the same letter. So we're still going to have to take the derivative. du over dx. And this is what? That goes away, and this is negative 5. So multiply both sides by dx, and du is equal to negative 5 dx. I really only have one thing. Remember now, we force it to fit what we need. We only have the dx. So we need this right side just to say dx. So we have to divide by negative 5. Notice it's multiplication. Don't add 5. It's multiplication, so we divide by negative 5. Negative 1/5 du is dx. We're actually making it bigger, but we have to, because we made this smaller, we got to finish the process. Okay, and that's going to help taking the derivative. So let me rewrite this. Integral of u to the negative 2 dx. That forces us to keep working. But now what can I put in place of dx? The negative 1/5 du. Here we go, integral of u to the negative 2, and this is times negative 1/5 du. In place of this, we're plugging in this, which is exactly what this says. And so it's not too bad because remember the negative 1/5 can go out in front. And now we actually have the integral of u to the negative 2 du. Okay, then we're ready to go. So all that, now we're ready to go. But this we can take the integral of. That we couldn't. So we had to rearrange it so it was something that we could work with. Add 1, divide by the new. So that gives us u to the negative 1, divide by the new. But don't forget that we also have this guy. Negative. At least the negatives are kind of nice. So these are just going to cancel. So we really have 1/5 u to the negative 1. And then you just have to replace what u is. 3 minus 5x to the negative 1. And then don't forget that is plus c. These are fine. Yeah. So because of the negative, you could move this down. And because the 5 is there, I left it like that, but you could even actually distribute the 5 if you wanted. That's kind of like, sometimes it's nice to have it factored, but you could actually 15 minus 25x. Any 3 of these are fine. They're all saying the same thing. I'm okay with any of them. Sometimes they don't like the negative exponent, but it's okay. What else? What else? Okay, and this finds you the area under the curve. So it's kind of like if you had to work with it, like tomorrow, if we have to find the area of the curve, then you can actually pick whichever one you like the best. That's just preference. Okay, let's do, okay, so we did that one. Let's do, either 1, 2, 3. Right, 4. Oh, 4 is, okay.
For the fraction, the 1 to the over 5x, whatever happened to that negative? It was -1, so that's why you have it like that?
Yes, so this, why was, oh, this was negative just because it happened to be a -5. And then because when we added 1, we had a -1, we have to divide by the new. And so this then becomes positive 1/5. Does that work?
Yeah.
All right, good question. All right, let's try this. This one's like the exact opposite. This one was really small. Take a look at one that's really big. See which one we like better. Integral of x squared plus 2, and then the square root of 6x plus x to the 3rd, and then dx. Yeah, okay, this one's not too bad, but there are a few tricks here. I think on the test, and I'll have to look, but I think on the test, I put in the directions, use U substitution. Because I don't want you to kind of like not know, should I use U substitution or not? So at least I will tell you when. Because I think they do that in the book as well. We're still learning this. This kind of becomes the norm, or we definitely use it a lot more in Calc 2. And since we're just learning it for right now, I'll at least tell you, I won't tell you the U on the test, but I'll tell you this is a problem where you need to use U. Okay. All right, so, but remember, the first few on the homework, they do actually tell you U. But let's just practice. So don't let that U, if they tell you on the homework, just go with it. Or try to cover it up and make sure that it makes sense to you that that is supposed to be. All right, so any ideas? What is the U in this problem? Something have an extra, a quantity with an extra piece. Okay, but what is its extra piece? Is there anything else happening to this besides the times? Nothing, right? It's just kind of hanging out there. But where's another quantity that is something else with it? Yeah, do you see? And what is the extra piece that it has with it? It has a square root. Now, do I take the square root as part of the U? No. But because it has that extra piece, now, if this had like something as simple as like a 5, okay, now that has an extra piece, okay? But because what is this? Remember, 6x plus x to the 3rd, that has an exponent. What is the exponent? 1/2, okay? So it's up to you, kind of, we can leave it like this for a while, but eventually we might do something with it, with that 1/2. But, and that's kind of the difference. The x squared plus 2 does not have anything else. So it kind of just tags along. But this has that exponent. I don't take the exponent with, but that exponent identifies that that's my U. Okay, so now we take the derivative. So derivative of u is du dx. What's the derivative here? Perfect. 6, take the derivative of this, 6, take the derivative of this, 3x squared. And then we just always multiply both sides by dx to get all the x's together on that one side. We've got 6 plus 3x squared, it's kind of like a quantity, and then times our dx.
We have to divide du by 6, or 6 plus 3.
Beautiful, yes. Okay, so now remember, so this, I'm going to write it, I think, with this exponent. But what, let's do it. 6x plus x to the third to the 1/2. And then this, I have this whole thing tagging along. So I have this, can you see that? This piece, and then this piece. So I just put them together, because those are kind of the two pieces I haven't really touched yet. If you even want, we could even do this. What can I replace this with? That would be u. But what's wrong with this? I got x's and u's, and that's a huge issue. You can do that though, it might condense things, and it kind of gets you focusing now on this. Yeah, she said, okay, I have to match this. I cannot change this. This I cannot change. Can I get this to match that? Well, I got the dx. There's a lot of similarities here. I have to factor out a 2. If I not factor out a 2, sorry. I have to factor out a what? Not a 2, I have to factor out a 3. So if I take out a 3, I'm left with 2 plus x squared. And even that isn't perfect, but it's addition, so I can just rearrange that. So this is the same as 3x squared plus 2 dx. That was kind of tricky. So you can't completely get rid of the 3. You do have to factor it out. And then now we need this side to match this perfectly. So what am I going to do over here? Divide by 3. Divide by 3. And now I have 1/3 du, but it equals x squared plus 2 dx. All right, so now we're good. U to the 1/2. This whole thing gets replaced with, I can just use the other side of my equal sign. That whole thing's going to get replaced with 1/3 u. And so now these two are considered the same thing, just that with that substitution. But now that bottom one, we can take the integral. So we can even move the 1/3 out. More just a visual thing. Now, just take your time with this. That's how we solve fractions. So add 1 takes us to 3/2. Now we're going to actually do the integral. Add 1, divide by the new. Now I have this 1/3. I can either divide by 3/2, or I can, perfect, multiply by 2/3, and nothing cancels. And that's okay. So I've got 2 9ths, and then u to the 3/2. You can put the plus e now or later because we still have one more step. We still have to replace the u. So now the integral, we added 1, divided by the new. We got fraction crazy stuff, so we're just going to multiply by the reciprocal, and then we just have to plug that back in. 2 9ths. U was 6x plus x to the third to the 3/2. And then that equation will find us area under the curve. Area under that original function. We can get a couple more in. This one's kind of like the previous one. We can get two more. This one just looks weird, as if the rest of it doesn't look weird, but let's take a look. Why do we say it looks weird? Integral of 3x plus 2 to the 3.9 dx. We probably, we probably could change that to a fraction, but it's just a weird fraction. Big fraction, right? And we can still take the integral of a decimal exponent. Okay, it kind of goes back to the first one because there isn't much to it. Which is that good? Is that bad? What is our u? Do we have a quantity where something else is has something with it? What's our u gonna be? Yeah. Say it again. Perfect. Yeah, right. So it has this extra piece. It has this exponent of 3.9, but we're just going to do the 3x plus 2. But because it has that extra piece, it's also the only thing. Just make sure you don't take the 3.9 away. Good. All right. And then as soon as you have your u, you take its derivative. Derivatives are going to haunt us. They're not going away. All right. And then we multiply. Oh, dear. We have to take the derivative.
So that's 3.
Yeah, what should that be?
3.
Just 3. Yeah, you're right. Yep, that guy goes to 3. Oh, yeah, that guy goes to 3. Good. All right, so that looks better. Make sure you make that just a 3. Go ahead and take the derivative. And then multiply both sides by dx. 3. Yeah.
And 1/3 du equals u.
Oh, that's it. Yeah. I mean, look, this whole thing is u. You still have to the 3.9. Just be careful because you still have the dx. So she said, hey, I just got to get rid of that 3. It's multiplication, so we're going to divide. 1/3 du equals dx. This is a weird one because we're actually substituting in more. Right? This is one thing. This is two things. We don't care how many things. It all has to be u now. We reduced this, which was so huge. That was such a big deal that we don't care if the dx has to grow a little bit. And because it's growing with a constant, you can carry them less, right? So u to the 3.9, and then it's 1/3 du. In place of dx, we're plugging in that quantity. We don't even care about the 1/3 because remember that can go out in front, at least for a little while. Everything's in terms of u. It's much smaller now as far as what I have to take the integral of. So overall, that's what we like. Add 1, divide by the new. Add 1 takes us to 4.9. And then divide by the new. So we've got 1/3 divided by 4.9. So you could do that with a calculator. 1/3 times the reciprocal is 1/4.9. So I made this guy, put it over 1, and then instead of dividing, multiply by the reciprocal. You could also just put it up here if you want, if that looks. But I made that 4.9 a fraction so that I could multiply them by the reciprocal. Okay, so that gives us what? Switch back to the black. It might be easier. I think it's easier to see the black. Oh, it's not. Okay, so that is what? 12 or 27, 14.7. So, okay. Okay, so now a couple things. Plus c, you have to remember plus c. We have to put back the u, so 3x plus 2. This answer is okay. Sometimes we don't like decimals and fractions, though it's fine with me. I'm not too picky. But technically, we could move this over 1 if we move this over 1, and so probably the best answer would be 10 over 147. But if you do a decimal and a fraction. Because another reason I don't care is because once I go to evaluate this, I'm going to be plugging in numbers and I'm going to be doing arithmetic anyways. So I don't care if it's 1 divided by 14.7 or 10 divided by 147 because I'm going to have to plug it into a calculator, right? So for me, that's it. All right. Let's do this one. This one isn't too bad. We can sneak in one more here. Integral of cosine of theta times sine to the 6th d theta. Okay, so what's our u? Kind of what gives it away? We're multiplying. We have a quantity. Anyone want to take a guess? Probably not a guess, but a try. What do we think u is going to be? What has that extra piece? You got cosine up there and sine up there, but which one has the extra piece? The sine. Don't take the extra piece with, so my u is just sine. Don't take that 6, but that 6 is telling me, it's like my nudge, hello, this is what you got to use for the u. Okay, so then we take the derivative. I guess in this case, it should actually be d theta. That bottom one is the x. So just try not to do the x in this case. It's I should say it's whatever the variable is. The bottom one should be that variable. Okay, now what is, remember here we're taking the derivative. What is the derivative of sine? Cosine. Derivative of sine, remember we're doing derivative. So derivative of sine is just cosine.
If sine positive, wouldn't that make cosine negative?
Not that for the integral. For the integral, that's when you do that. But for regular here, don't forget here we're actually doing derivative. So derivative of sine is cosine. Yeah, that's a good call. And actually, I don't think we're going to take the integral of trig. This is going to be crazy. All right, so we multiply both sides by d theta. So we have du is equal to cosine of theta d theta. So this guy's the one I use. Sometimes I move that to the front so I see what's left. I have not touched this. I have not touched this. So I'm just going to rewrite it, cosine of theta. Remember, too, a lot of times we put the smaller thing first. Well, a lot of times that middle piece is actually your u, because your smaller piece goes to the front, and then once the middle becomes the u, then I like to rewrite this together. The stuff I kind of touched yet. This sine to the 6th, this is going to become u to the 6th. And we get to hug trig in this problem, right? I mean, we did have to do this one. But look here, cosine theta d theta, cosine theta d theta, I don't have to touch anything. What's going to go in its place? du. All that goes away to du. And I actually end up taking the integral of u to the 6th. I don't even actually end up taking the integral of the trig. So this matched perfectly. Every once in a while, stuff will match perfectly, which is great. I don't have to touch this. I just place in du. Now I'm actually adding 1 divided by the new. Add 1 divided by the new. And then a couple things. We've got to do plus c. And we can do sine, because sine was u. Sine to the 7th. 7. If you have the one, if you wrote the 1/7 like this, beautiful. That's fine. It doesn't matter. Okay. And remember, this 7, this is just a reminder, usually this is how we write it, but if you have sine of theta to the 7, that means the same thing. Which may have helped maybe up here, but if that kind of threw you off, parentheses, it would be sine of theta to the 6, and there's kind of that exponent, which reminds you that's your u. Okay, so we're over. So let's stop there. You should. The hard thing is kind of each one's a little bit different, but you should be able to do your homework. Give it a try. If there's a few that weren't examples, try them. We'll have a little bit of time tomorrow. Tomorrow we're just doing the same thing, but we're going to have to evaluate it. Just a little bit longer. So the same concept though tomorrow. All right.